to me. And again, as I said, maybe the last time, because I'll be teaching heavily starting next year in physics, or going back to physics from oncology after 15 years of oncology. Time flies. So this will be a series of 4 lectures. Some of it is the same material that I covered last year, but there'll be a lot of new things because I had more time. And it will be in the following sequence, roughly. The first lecture today will be a historical perspective. I don't know how many of you took quantum physics. I assume none. So it'll give you a chance to hopefully understand the foundations of quantum physics. And the reason for it is that, of course, first of all, it's being used now in the context of biological systems, so you need to know what are the tools. And secondly, because I see strong historical parallels between physics roughly a century ago and biology/medicine today. So that's the 100 years gap. Physics arguably is the most advanced of all the sciences. Some people even claim that in science there's only physics and the rest is stamp collection or collecting. I'm citing somebody famous. But biology right now is exploding, and it has a huge amount of data to sift through, but there is still a missing conceptual framework which physics built over 3.5 centuries. Now, we'll talk about whether there is room for quantum or not, but that's basically the idea. The next lecture Thursday, will be on actually molecular level of biological systems where quantum effects are suspected to be happening, have been seen, and so on. And then the last 2 lectures will be one on quantum metabolism and one on neuroscience and the human brain, maybe consciousness, and a little bit of developmental biology, which is also implicated in some very intriguing quantum effects. I do have some credentials in this area. These are 3 of the 12 books I wrote or co-wrote, and this one on nanoneuroscience delves into the area of nanoscale neuroscience, and this is what the playground for quantum effects may be taking place. We don't have precise enough tools to be able to see it. And then there's the emerging physics of consciousness and biophysics of consciousness, the most recent book on the right. And you can find a lot of material there. I think the last 2, or maybe all 3, can be downloaded free from various places on the internet. And if you're interested, I can probably give you access to that material. Okay, so let's start the first lecture and talk about physics. So, because this is a worldwide audience, I'm sure somebody will find it interesting, maybe not you, but somebody out there will find it interesting. So let's start in the historical context. So quantum mechanics was born at the turn of 19th and 20th century, so 120 years to the day in 1900. But what was before was already incredibly solid and highly useful and applicable, and that included classical mechanics, which gave rise to all aspects of engineering, mechanical engineering, civil engineering, and so on, through the discoveries of Sir Isaac Newton and others who came after him, Lagrange, Hamilton, Legendre, and many other names that played a major role in developing one of the most elegant areas of science, classical mechanics. After that, electromagnetism was built from empirical observations by Ampere, Faraday, and again constructed into a virtually closed conceptual edifice by Maxwell. And Maxwell's equations describe basically all of electromagnetism, all these phenomena under one umbrella, and we use it today in cell phones and computers and you name it, all of technology that, plus more recent discoveries, as you will see, entered into this, into the building of that field of physics. And then again, most of it that followed was a result of technological demands and sometimes military demands and sometimes economic demands. Physics is developed as a field of great importance to technology, and no exception was thermodynamics, which was built roughly in early 19th century and up to the mid 19th century with the first industrial revolution required machines, engines, locomotives, and trains, and all this, and that was the result was the field of thermodynamics built by Gibbs, the most famous American scientist until then. And then Watt, Carnot, Thomson, and Clausius contributed greatly. And on that basis, actually, this thermodynamics is phenomenological. It's not basic science, just like electromagnetism is really fundamental, but thermodynamics is more empirical. But statistical mechanics gives the conceptual foundation to thermodynamics, and that was developed by Boltzmann and Nernst and Helmholtz, and some of these names you will find also in biochemistry and biophysics and cell biology, because thermodynamics and statistical thermodynamics play a role in things like biochemical reactions and chemical affinity, so all of it is hugely utilized. All right, so that's, at that point, at the end of 19th century, everybody was very happy with the progress, and it seemed like the rest was, what needed to be done was basically engineering, not physics. In fact, there was, and I'll come to it in a minute, a great conviction that there was basically nothing to be discovered. And how wrong were they? We now know. On top of all of this, physics, the language of physics is mathematics. And luckily for physics, brilliant mathematicians developed the tools to describe physical phenomena. And these are the key tools that entered into these various fields, including quantum mechanics. Quantum mechanics, as you will see in a minute, heavily dependent on functional analysis, the algebra of operators, and solutions of partial and ordinary differential equations. All of this was available due to the great discoveries in mathematics in 18th and 19th century. It's kind of an interesting sociological observation that discoverers or scientists in various fields blossom at different ages. So mathematicians, usually the most brilliant mathematicians, achieve their greatness before they hit the age of 30, 26, 25, sometimes 19 or 18. This is amazing. In physics it's a bit later, but not that much. Maybe 35 or so. And then biology and more complex fields require maybe more maturity, not so much sheer brilliance, but being able to assimilate different contributions from various fields. So perhaps in biology, medicine, you can make great discoveries later in life. But anyway, so some of these mathematicians were incredibly young by today's standards. Okay, so as I mentioned to you, at the end of 19th century, there was a great feeling of accomplishment and basically satisfaction with the status quo. And so Albert, this quote is usually attributed to Lord Kelvin, which is wrong. It's actually Albert Michelson who came up with this idea. He got the Nobel Prize for the experiment that demonstrated the speed of light with Michelson-Morley experiment, which actually Einstein wanted to do, but they were first, and they got the Nobel Prize. He got his as well. And you'll today, actually, the whole lecture will be about Nobel Prizes, pretty much. Every name I mention is either a Nobel Prize winner or somebody who should have been, because it was too early to win Nobel Prizes. But Michelson said, it seems probable that most of the grand underlying principles have been firmly established. The future truths of physical science are to be looked in the 6th decimal place. In other words, we'll just be finessing some corrections. We know everything that's to be known. You know, the foundations are laid. The rest is just 6th decimal place corrections to our measurements. And that of course was at the end of the 19th century, and a couple decades, maybe even, not even a couple decades, a few years later, several scientific revolutions occur. There's actually a course in physics on scientific revolutions, and some of them are in physics, some other ones are not. But the ones that occurred in physics are the top 3, all of which have a bearing on quantum physics. Special theory of relativity by Einstein, then general theory of relativity by Einstein, and quantum mechanics with participation of Einstein, but mainly built by others, Max Planck and Erwin Schrödinger and Werner Heisenberg and Pauli and Dirac and others. You'll hear these names. As I mentioned, every single name mentioned here is a Nobel Prize winner. So these were fundamental discoveries in physics, which then percolated into chemistry. Chemistry is basically quantum physics because there are no chemical bonds without quantum interactions between atoms that enter into a molecule. So that's an extension, but then there was fundamental development that goes beyond quantum physics. You'll see in a few minutes why it is more profound, called quantum field theory. That's the greatest achievement, and you've heard about this, probably about the standard model, basically trying to include all the physical forces under one umbrella stemming from a single underlying conceptual development. But let's not forget what followed was actually not in physics, but in biology and biochemistry, discovery of DNA, foundations of genetics, molecular biology, structural biology, all of these revolutions that occurred in the second half of 20th century have nothing to do with physics, but maybe they do actually. We just don't know. So that's a hint of quantum biology becoming maybe in the next, revealing itself in the next decade or two during your lifetime, I hope, maybe not mine. But anyway, that's the logical sequence of events leading up to today, and in the last 120 years, we are seeing sort of gradual penetration of physical ideas into other fields. And I'll mention some of them in more detail than kind of a throwaway sentence or two. So from classical physics, and in a few minutes you'll know what the difference between classical and quantum physics, to quantum physics, from quantum physics to quantum chemistry, from quantum chemistry to perhaps quantum physiology and quantum biology. Now, of course, you hear every day about quantum computing, which will revolutionize all we do in our society, the speed with which we operate technologically, access to data, management, recognition, pattern recognition. Everything will change. And we are mimicking perhaps the brain, so quantum brain or quantum neuroscience. I'll say a few words about anesthesiology, which is an incredibly interesting field. Probably somebody said that this is the greatest medical advance in the history of mankind because it allows all the surgeries and modern medicine wouldn't function without anesthesiology. We still don't know how it works. What is the underlying mechanism? And I'll try to argue later, maybe in the third lecture, that anesthesiology actually is a manifestation of quantum biology at the most tangible level, switching off and on consciousness. And finally, a bit more adventurous. You mentioned that we can be adventurous in this course and forward-looking, futuristic. Why not from here jump to psychology and even psychiatry? I think physics, if not taken literally, it can at least give you conceptual tools to think about these things more elegantly and and even mathematically. Okay, so now for the rest of today's lecture, I'll just guide you through the development of how quantum physics came about in practical terms and what it proposed and why it occurred in the first place, because it was a need for it, not because somebody was sitting in an office, got a grant, and had to spend the money and came up with some crazy paper. No, it wasn't like that. And the science changed a lot. I lament the departure from this pure curiosity-driven scholarship that took place in those days, as opposed to today, where everything has a monetary value. You don't do any research unless somebody pays for it. Right? We've become mercenaries. I'll be throwing in comments like that from time to time, so stop me. So, anyway, historical timeline is about 4 decades, starting from 1900, when Max Planck introduced the idea of energy quantization to explain black body radiation. You'll see what it means. And then 1905, Einstein explained the photoelectric effect. He got a Nobel Prize for this, not for the more, I would say, more important, more revolutionary discoveries of special relativity and general relativity. He should have been given 3 Nobel Prizes, at least. And in fact, another little anecdote, if you don't mind. He got one of the smallest Nobel Prizes in terms of the value, because the value changes depending on the rate of inflation and the interest rate, because it's a fixed amount which brings in annual returns, right? And at that time, I think he got something around $350,000 US in today's money, which is probably about a third of average. And in fact, all of it he donated to his ex-wife. And so he got exactly $0 for his Nobel Prize, personally. I was in Sweden, in Stockholm, in the Nobel Museum, and there was a letter to his wife in which he's, prior to obtaining the Nobel Prize, he said, in the unlikely event that I get the Nobel Prize, I will give you the funds so you can buy a house in Zurich for you and my son. So his son, they divorced, and that's what happened. Anyway, so that's 1905. Then 1913, Niels Bohr explained atomic emission and absorption spectra. Then Louis de Broglie introduced the idea of wave-particle duality. And this is so-called wave mechanics, or old quantum theory. And from 1925 on, it's the actual quantum mechanics. The name changed, and from empirical, it became conceptual and mathematical. And this mathematical formulation, or several formulations, were introduced starting in 1925 with Heisenberg and Schrödinger equations. They developed equations which are equivalent, roughly speaking, to Newtonian equations, Newton's equations of motion for mechanical objects. And these two people, Heisenberg and Schrödinger, came up with equivalent mathematical descriptions for quantum objects. Schrödinger introduced the wave function, and Heisenberg did this for operators. And then in 1927, Heisenberg formulated the uncertainty principle, which is very profound and very philosophical. We'll spend a few minutes about it, talking about it. And then 1927, Dirac introduced relativistic concepts. So 2 revolutions merged into one. Paul Dirac unified quantum mechanics and special relativity. In other words, he allowed quantum objects to travel with the speed of light opposed to it, and until then it wasn't possible. And then John von Neumann refined all these formulations. As you know, he's the creator of computer science, pretty much. And he also participated in the quantum revolution and actually foresaw quantum computing about a century before it happened. So a lot of visionary people. And then 1940, this is the birth of quantum field theory. Feynman, Schwinger, and Tomonaga introduced quantum electrodynamics. Okay, some interesting characters. One day I'll write a book about these people because they're so interesting, like Feynman especially. He was quite a character, an American physicist with a lot of panache and incredible sense of humor. Schwenger was, for example, his PhD thesis was never published. It was, today it's impossible to get a PhD without publication. He just wrote something which is so unique, so original. Nobody could understand at that time. Right. So this was the greatest gathering of intellect on this planet ever, I think, in one place. I'm not dismissing the ancient Greeks, but I don't have that much knowledge about ancient Greece, a little bit, but here in this photograph, I think maybe without an exception, perhaps with two exceptions, everybody here got a Nobel Prize, and one person got two, namely Marie Curie. Is this a?
Yeah, you can turn it on and then you'll be able to use it. But you have to point it at.
I'm standing so close, so maybe I'll use a pencil or a ball pen. So this was a series of conferences organized by a chemical company, Solvay, in Belgium, and to promote this new area of science. And it took place in a hotel I visited. I spent a year in Brussels, and it's called Hotel Metropole. It's like a grand old. Okay, great. It's like Hotel McDonald, very elegant. And these people, including, actually, so this is Schrödinger, this is Sommerfeld, this is Heisenberg here, and you have Einstein and Jordan and Marie Curie and Planck and so on. So they basically came together to discuss and codify the new field and generate a common platform. And that's, so this was, I think, 2 or 3 conferences in a row, and they came up with this foundation of quantum mechanics. Okay, so that's the historical. Now we'll go into the nitty-gritty a little bit. I mean, you should take 3 courses in physics to really get into the nitty-gritty, but we only have about an hour or less. So, as you probably know, in classical physics, we talk about material objects with mass, and you can characterize their position by coordinates in 3-dimensional space, x, y, z, and time, and they are moving with a velocity v and acceleration a. And Newton basically described the motion of any such object in the presence of fields like gravity, for example, or electric fields, so there is a charge, and you can solve Newton's equations of motion and predict the movement or trajectory of any object, and that's why we can send satellites into space, because we can solve these equations. Now, of course, with relativistic corrections, but okay, so that's highly predictable and fairly easy if you know a little bit of math, which, by the way, Newton introduced himself because he needed the math, so he created calculus, as you wrote. Okay, so on the other hand, we also in classical physics we have waves. So we have particles and waves, and waves are not necessarily material translocation, but movement of amplitude in a medium. This could be an ocean wave. We call them oscillations in space and time, because they are periodic changes of position of any particle as a function of time, so it goes up and down, and space. It has a period and wavelength, which is the peak-to-peak distance. So wavelength, frequency, is the inverse of peak, the period, velocity, amplitude. So that's in classical terms, but you'll see how it translates into quantum. So the difference between particles and waves, or many differences, but the key one is that particles collide and they can either bounce off each other or they can stick if these are inelastic collisions. But they cannot penetrate to each other. And this is the property of waves. Waves can penetrate through each other and pass through or scatter off. And the waves spread in time and space. Can be superimposed, so you can add wave up on top of another wave, just like a sound wave. I'm talking and there is something coming here, and you can be chatting if you want, and all these waves add up, right? They can interfere sometimes with each other. That's why you have sometimes problems with the radio when it's not perfectly at the proper frequency. On the other hand, particles are localized in space and time and move as one unit. They cannot pass through each other. And so quantum mechanics basically, as you will see, changes this whole clean separation between particles and waves. And in quantum mechanics, an object can be both a particle and a wave at the same time, depending on how you look at it. Okay. But before we can introduce this kind of thing, we have to look at the need for it. There was a clear need, and this need arose from experiments that classical physics, which I explained to you what consisted of, classical mechanics, electromagnetism, thermodynamics, and so on, was unable to explain. Only a handful of experiments. So it wasn't like suddenly an avalanche came and swept everything away. In biology today, I think it's very similar. There's a handful of very awkward experiments we cannot really properly explain, and some concepts are not really gelling together very well. So in physics at that time, these were the 6 key experiments that changed the thinking of physicists. Atomic emission and absorption spectra, sharp lines on the frequency or wavelength scale, indicating what type of electromagnetic radiation was affecting an atom or was emitted from an atom or molecule. Discovery of electrons orbiting the nucleus in atoms. Black body radiation, actually that was the first one historically. And many of these things were known for a few decades and still nobody could really explain. The photoelectric effect, specific heat of solids, and Compton scattering. So Compton scattering I will not spend too much time on, but it's quite interesting because it really demonstrates directly that waves and particles are not distinct. They are one and the other at the same time. Because X-rays, which are high energy electromagnetic waves, when impinging on stationary electrons, would put them in motion. So electrons, which we think as little ping pong balls, would then start moving and get momentum and energy from waves. So that's the Compton experiment, Compton scattering. So quantum theory in essence means that systems, physical systems or quantum systems, exist in discrete energy states. That's why it's called quantum mechanics. Quantization means discrete levels. By and large, I mean there are some exceptions, but that was the first noticeable difference between classical systems. In classical systems, you can think about a continuum of energy levels, right? So I don't know, a mechanical engine can crank up the speed and therefore the energy output arbitrarily. But in quantum systems, you can only have discrete levels of energy. This is really fundamental and weird. That is, in quantum physics, you cannot distinguish between the system and the observer. In classical, you can probe a system and find out by delicate measurements what is the velocity, Doppler radar or any other scan can give you access into the information about the speed or velocity or energy or things like that. in quantum mechanics, the observer, there's no way of gently interrogating a quantum system without disturbing it. So that you cannot separate the observation, the event of observation from the system itself. And then, so quantum systems are non-deterministic, and this is a philosophical revolution affecting our understanding of the universe. If you think about it deeply enough, that means that no system, not even the smallest system, can be completely predictable, and that is counter the reductionist, deterministic worldview up until then, going back to Simon de Laplace, who said famously, having studied classical mechanics and contributed to it, that if you give him the coordinates and velocities of all the particles in the universe, he'll predict the fate of the universe. And this was very boastful, but completely idiotic. From today's point of view, of course, then it was different. And now we say that you can't even predict the fate of a single electron, let alone the universe, right? So think about this, and this is also in terms of singularity. I think there is some philosophical underpinning here. All right, so Niels Bohr, who was one of the greatest quantum physicists, stated that anyone who is not shocked by quantum theory has not fully understood it, because it has such repercussions on how we view the world. Of course, we have no intuitive understanding, because this is not how we are experiencing the world. But it's only because of our limitations. Our senses are so limited in terms of perception, right? The vision is great, our sense of vision is great, but it's only exploring the wavelength of electromagnetic radiation from 400 to 750 nanometers. We can't see anything which is ultraviolet or infrared. We can't see it. And it's only a sliver of the electromagnetic, for example. Right? The same with the sense of hearing. We only hear acoustic waves, vibrations between 20 and 20,000 hertz cycles per second. You know about ultrasound going into megahertz and so on. So we don't have the access through the senses to a lot. But if you use physical instruments, you soon discover that the world is not deterministic by any stretch of the imagination. Okay. And Feynman, I mentioned to you, he said, things on a small scale behave nothing like things on the large scale, which is what we experience. I hope you can accept nature as she is, absurd. Okay. And Einstein never actually, he never actually accepted quantum mechanics, because he grew up in this classical worldview where everything was predictable and so on. He didn't believe that God plays dice. Okay, so now what are the basic assumptions of quantum mechanics? You remember the Solvay conference in Brussels, 1927, 6 and 7? These conferences came up with the postulates to basically codify the field. And we'll go through the postulates. For the longest time, it was believed that quantum mechanics applies only to microscopic objects such as atoms, electrons, neutrons, subatomic particles, but nothing greater than that. Now we know that chemistry, which is molecules, even macromolecules, requires quantum physics to understand how these molecules are built and how they work. But it's more than that. I'll mention to you in a few minutes macroscopic quantum phenomena, that is, phenomena on the scale that we can touch and experience. But until recently, most of it was thought to be limited to elementary particles. I'll come back to it. So the basics involves this wave-particle duality I told you about. There's no clear distinction between waves and particles, because particles are actually wave-like. You can think about, in the context of quantum mechanics, about particles as clouds, but clouds which may have different range of their gas density. And quantum mechanics uses the language of probability theory, which I will explain to you in a second why it is so. And I mentioned to you the observer problem, that there is no, and actually this is a very, almost Taoist, I think, issue, that does the world exist, matter exist without the observer? If there is no experiment that can be giving you a glimpse into the physical objects without interference, if there is no interference, does this object exist? You don't know. So that's the observer problem. But it has been also believed that the quantum fuzziness, if you will, cloudiness or fuzziness of quantum objects disappears gradually as objects become larger and larger. So at our level of perception, maybe nothing is quantum, but maybe not. Okay, so I mentioned this already. Simon Delplace, quantum world is probabilistic, and that was actually a big problem at the time, because there was no clean connection between mathematical descriptions, equations that Schrödinger and Heisenberg and others came up with, and observations. So how do you link measurement to the actual reality of the system? And then the Copenhagen interpretation was postulated by Niels Bohr and others, which means that there is actually a nice connection. You will see in a second again. But again, I'll very quickly go through the milestones in the quantum physics. I mentioned some of them. The first one was actually the discovery of the electron. And as you now know, everything that we touch is involving movement of electrons. Until then, the world didn't know about the existence of electrons. And then radioactivity, which is that atoms may be unstable. Isotopes could break up into others, and that's of course the also quantum mechanical, because instability of atoms cannot be explained by classical means. So that's, yeah. And alchemical transmutation, you can make different elements from others if they are unstable. And then this is the Louis de Broglie. He was a French count, actually. And he didn't need the money. And actually, he didn't even study physics. He wrote the PhD thesis and got a Nobel Prize for it because it was so groundbreaking. And he developed the wave-particle duality concept, that at this level, everything is both a particle and a wave, depending on the observation that you make. And based on this, you can, today you have applications of this idea in things like electron diffraction. Crystallography allows you to view matter through scattering of electromagnetic radiation and obtain images. He introduced in his thesis, and Nobel Prize winning thesis at that, the concept of wavelength of a particle, which is kind of, in the classical terms, oxymoron, right? A particle is a particle. How can you have a wavelength of a particle? It's not, well, it is a wave. So that's the definition. Lambda, the wavelength, is equal to the Planck constant, h. I will introduce it in a second. Not everything is so linearly ordered in these slides, but anyway, it's the Planck constant divided by the momentum, which is mass, times velocity. So, so the smaller objects will have long wavelength, and also slow moving will have longer wavelength. Okay, so this Planck constant is named after Max Planck, who actually was pretty old by those standards although the photograph from Brussels looked at a bunch of old people, but I think they were like 27 years after Max Planck discovered his quantization principle. So at that time, when he discovered it, he was one of the most highly regarded physicists in the world, and he was 42, I think. So an old guy at 42. But Okay, so that's what he, to explain black body radiation, and I'm not going to go too much into the math behind it, but there are formulas, and this is the formula that he introduced, which is H times F. Very simple formula. It tells you that the energy of a wave is proportional to the frequency of the wave. Very simple. And it's just a linear relationship that changes everything. And in order to fit it into the data, he put in a constant called H. It maybe should have been called P, Planck, because it's the Planck constant. And that explained it, and perfectly, in fact. So that led to this famous quantization equation. So the energy of any electromagnetic, well, let's call it quantum, is equal to what I said, H times F, but not an arbitrary number. You cannot have, 1.72 times this. You can only have n plus a half. N equals 0, 1, 2. Actually, that should be a 0. 0, 1, 2 up to infinity. And 1/2 actually is another bizarre thing in quantum mechanics, which is the ground state, the lowest energy state in classical physics could be stationary. It's like something sitting, this chair has no kinetic energy, it's sitting here. All right, that's zero energy. It's like moving, now it has some velocity as energy, kinetic energy. Or a car, right? If you park your car, there's no kinetic energy. If you start driving, now it has a lot of energy. But in quantum mechanics, the lowest energy state is not zero. In quantum mechanics, subatomic particles have always some energy. It's called zero energy, 0-point energy, which is 1/2 H times F. And some people today even speculate that there is infinite amount of energy accessible. If we can figure out the technology that could get access to this energy, every particle has energy, which even if you don't deliver in any means, electromagnetic or thermal, it has this 0-point energy. But anyway, that's the formula that gave Planck the Nobel Prize, because of this, really. I mean, two things. Frequency is, the higher the frequency, the higher the energy. And the second is n, that you can only have integer quanta, 1, 2, 3, 4, 5 quanta of electromagnetic energy. You cannot have 2.7. All right. Since we can't access this, sometimes this 1/2 is dropped because it's just for elegance sake, but not for practical sake. So these are the spectra that people knew it, actually going back to 1868 or something like that, for 3 or so decades they were measured. These are the power intensity of emitted electromagnetic radiation from objects at different temperatures as a function of wavelength of the electromagnetic radiation. So you can see that the peak wavelength is inversely proportional to temperature. And that was not explained until Max Planck came on the scene and postulated the formula, and everything then was solved. And it wasn't, and it wasn't a small thing. It was really groundbreaking because it shattered the foundation. Then you have to think about why is there an integer n. Until then, everything was continuous. It's like a dial. You can dial any station on the frequency range. But here it's 1, 2, 3, 4, why? And that came up later on when Schrödinger postulated an equation which was replacing Newton's equation. But the second experiment, you probably know about photoelectric effect, and we see it every day. Photocells basically involves 2 electrodes, metallic electrodes which can emit electrons when light strikes this plate, only when the frequency is high enough. That is, you remember now, energy equals h times f. So if high energy, frequency means high energy. If frequency is high enough, energy is high enough, and this energy of light is given to the electron to be ejected from the surface. And then this electron can travel to the opposite electrode, the cathode, and you can measure the current that flows through it. So that's basically the mechanism behind the photocell. And the explanation here that Einstein gave and got the Nobel Prize for is, again, it's a wave-particle duality aspect, because light, until then, of course, was considered to be a wave, electromagnetic wave, but the electron is ejected, so gains energy by absorbing the energy of a wave. And so that these two things occurred simultaneously, and also on top of that you have an energy gap the electron has to overcome in order to be ejected from the plate. All right. He wasn't that old then. I think he was 32, if I remember correctly, when he discovered the photoelectric effect. And actually in 1905, this is a very important year in physics, Albert Einstein was employed by the Swiss Patent Office. He couldn't get a job. He got a PhD out of the Swiss Federal Polytechnic in Zurich, and he was second from last from the graduating class of PhDs, and unemployable basically with a useless PhD. And only because of his friend's connections, Marcel Grossmann, who was his friend in this class, and his father was in charge of the Swiss patent offices, and gave Einstein a job as a clerk in the examining patents in this office. And I think he spent a year and a half maybe, and that was the most productive year in his life. He didn't have an academic position. He didn't have a grant. He had no credentials, no prior publications, and he wrote 3 most fundamental papers in the history of physics. One of which was this, the photoelectric effect, and the other was special theory of relativity. Because in the patent office he was working on synchronizing clocks at different train stations. And so at that time there was no GPS, there was no satellite, of course, and there was a problem how to synchronize, no time zones, by the way, right? How to synchronize clocks at different train stations. So, and he actually wrote a patent on that. But as a byproduct, he understood the relativity of time and developed a theory. So, of course, I'm not saying that we should abandon the scientific system that we have today, and because not every physicist is an Einstein. But I think we should definitely encourage people to think like him. All right, so that's this idea of different wavelengths. Red would be, in this case, low frequency, so low energy, therefore there's no emission of electrons, and blue would be sufficient, and that's the amount of energy that you need for the electron to escape from this well. And this is the insurmountable gap in our understanding of the world that Werner Heisenberg came up with. There is no way around it. It's actually a completely fundamental formulation of our inadequate knowledge about the universe, irrespective of any experiment. Comes out of the fundamentals of quantum theory. So basically, what it says is the following, and it was first formulated for the position and momentum. Momentum is mass times velocity. So you can think about this as the ability to measure a position. So what you are sitting here, I can definitely put this on the GPS and give the coordinates to your chart. And if you were moving, I could maybe measure your movement, the velocity, and figure out, with some accuracy, there's always amount of accuracy. But at the level of quantum objects, the product of our lack of knowledge, our uncertainty in position, and the lack of knowledge about uncertainty of momentum or velocity has to be greater or equal than this number. Again, we see the Planck constant. So it turned out that the Planck constant, which at first was introduced like a fitting parameter, fitting to a curve. You do curve fitting in medicine, biology, you get from patient data, whatever. You find a straight line and you get a parameter, a slope or something. And that was introduced just like that. It turned out to be a completely fundamental physical constant which cannot be explained by anything else. And such as the speed of light also is a fundamental physical constant that cannot be explained from other first principles. So this is a fundamental relationship which tells you that there is a limit on our knowledge about every single object we measure. And it has to be uncertainty, so lack of knowledge about the position and velocity simultaneously is limited by that. And by the way, there are some other formulations. I don't have the time to go into the details, but the same applies to what we call in physics complementary variables. Position and velocity are complementary. In quantum mechanics, it's properly defined by commutation relations. Also, components of angular momentum. So a rotating object will have an angular momentum, and x and y and z components. They cannot be simultaneously defined or determined. But more importantly also, which is again of philosophical significance, we cannot precisely know at the same time the energy of an object and the time at which that energy was measured. So energy is very important physical determinant of a system, how much energy. And we don't know we cannot know precisely time and energy or position and velocity at the same time, anything. So that throws a monkey wrench into reductionism and determinism and all of this. Okay, I mentioned, maybe not, Rutherford, he was a bit earlier, I think he came up with this model of the atom, that there is an electron, I mentioned that, so let's go, move on. And that led to Niels Bohr's mathematical formulation of atomic energy levels. And you know, this is actually something that is very important to mention, because when Rutherford determined that there is an electron trapped, so to speak, within the proximity of a positively charged nucleus, electrons have negative charge. According to electromagnetism, electrons should basically collapse on the nucleus and coalesce, but it doesn't. It's separated. So classical mechanics cannot explain the simple thing, that the atom is constructed the way it is. And so Niels Bohr introduced this quantization idea without which electron would collapse and radiate energy away. So you must have seen this. You have the atomic orbits for electrons, and electrons in atoms, any atom, can jump between orbits. If they're given energy, they can jump away from the nucleus, and if they jump down, they emit electromagnetic. So this is emission spectra and absorption spectra. If an atom absorbs energy, the electron, 1 or 2 sometimes, will move away from the nucleus, but only to these finitely described orbits. They cannot sit in the middle between two orbits. So that's another example of quantization, right? That's why it's quantum, because it has to be one quantum, another. And that allows us the precision to be able to determine, for example, the composition of distant stars. Because light that is coming out of distant stars is emitted from these kind of transitions. So we know what sort of elements must be there in order to provide us with this emitted electromagnetic radiation, the wavelength or the frequency. all right? So that's one example of a concrete application. We can, just by examining the light coming from distant galaxies and stars, we can find out the composition. All right, so, and of course the same applies to molecules, and this was done by using the prism, analyzing the different discrete lines. Molecular spectra, a bit more complicated because as opposed to atoms, molecules can have other means of energy absorption or utilizing energy, including not just electronic transitions, but also vibrational modes. They can vibrate, like for example, CO, carbon monoxide, so they can move like this, or carbon dioxide, you can have rotational, vibrational, and many other torsional motions and so on. So each of these, by the way, and maybe this is not so obvious, but each of these things is quantized. You cannot think about rotational motion and think, oh yeah, it can rotate at any frequency. No, these are also quantized. Vibrational as well. And it's good because this allows us to figure out, for example, if there are any pollutants in the air, exhausts from cars and so on. What is that? Because these molecules have signatures, spectroscopic or spectral signatures. Pollutants, pigments, in paint, composition of stars, and of course, metabolites. And in terms of medical applications, you can spectrally determine the presence of different metabolites, sometimes pathological. Okay, pathology, right?
Yeah.
All right. I'll skip this. I mentioned earlier that this formula by de Broglie allows you to figure out how large is the wavelength compared to the object, and then the object's mass becomes very large. For example, you running a 100-meter dash. You'd figure out, I mean, I don't have the time to go through the numbers, but you can plug in, that's a very small number, and it turns out that your wavelength as a microscopic quantum object would be something, ridiculously tiny. Smaller than the size of an electron. So obviously we don't see ourselves as clouds propagating through space because of the size. I mentioned the Compton effect. There was one more, which is not trivial actually, very important. Spin is a quantity that only exists in quantum mechanics. It doesn't exist in classical mechanics. Electrons and neutrons and protons have spin, which means that they have a property, and again it's quantized. Spin can only be 1/2 or -1/2, up or down. You cannot have sideways spin or some angle. So quantum mechanics introduces this, and why is this important? Because without spin, there's no magnetism. And how important magnetism is, I mean, we use again magnetics, circuits and magnetic components in all the electronics. There's now a new technology being developed called spintronics. So instead of just electronic conduction, you have spin waves, that give you these, 0-1 transitions. And of course, you understand spin being up or down is like a bit. There's a quantum bit or qubit. So it's going to enter very soon probably into quantum computing, if it hasn't yet. So this experiment determined the Stern and Gerlach, two German scientists, they determined the presence of spin in electrons, and then later on in other particles, as a quantum observable or variable, which doesn't exist in classical systems. But magnetism is a macroscopic quantum phenomenon. I wanted to mention, this is important. This is one example where you can buy a piece of magnet at Toys R Us, or if it still exists, I don't know if Toys R Us still exists. But you could buy a piece of toy magnet, which you could play with and see how it attracts other magnets or repels, or so on and so forth. And yet, its existence has been known to the ancients. Magnetism was known to the Greeks and Indians and ancient Indians, and it's a quantum. There is no two ways about it. It's a quantum phenomenon. Okay. We have about 15 minutes left. We'll go very quickly through the postulates. This is the fruit of these conferences in Brussels, postulates of quantum mechanics. You cannot derive them from anything below. There's nothing that can guide you. Just it was a consensus decision on the part of the Nobel Prize winners, and then later on it was proven to be correct. We don't have any proof that it's not correct. So the first postulate of quantum mechanics is that, unlike in classical physics, quantum objects are described by wave function, an abstract mathematical concept. We'll call them phi or psi. A wave function it's not position, it's not momentum, it's not velocity. It's a wave function, but it has a meaning. It describes a state. And what's very important about it is a special wave function. There's mathematical properties, I have no time to go into it. But what's important is that if there are two wave functions that a system can exist in, or 4 or a million, the system can exist at the same time in all of them. In other words, it's called superposition principle. So quantum system can be simultaneously in many states, which is a complete no-no in classical physics. You cannot be here and in New York at the same time, right? I tried, it didn't work. So that's Erwin Schrödinger. He introduced the concept of the wave function. And the wave function's meaning is that this square of this wave function, actually it's modulus squared, is, according to the Copenhagen interpretation, is the probability that this system is in that state. So suppose psi is the probability that electron has spin up. Square of that is probability that has spin up. In this case, it can only be up or down, so the other one minus the probability would be this spin down. This name is important in the context of this set of lectures. Erwin Schrödinger, it's a very important date. I like history, I don't know about you, but if you don't know history, as somebody said, you're doomed to repeat the mistakes of the past. 1933 is the year that Hitler came to power in Nazi Germany. Schrödinger was Austrian, but his wife was Jewish, and they had to leave Austria, which was annexed by Anschluss in 1936. Became part of Germany. And he spent the Second World War years in Dublin, Ireland, which was neutral, by the way, at Trinity College. And he wrote in 1944, at the sort of peak of battles raging all over the continent, he wrote a book that I highly recommend to read. It's still valid today. It's called What is Life? And he spent the war years thinking about life and what is special about living systems, biology, the foundational aspects of biology. What's so special, you know? And so he has he played a role in physics, of course, huge, also in biology, and coincidentally had 2 wives. So maybe that's kind of parallel. Life imitates art, art imitates life, kind of thing. 2 wives at the same time, not like a superposition state, right? Okay, so we talked a little bit about this wave function. Wave function contains all the information, but this is not complete information. It's a probabilistic information about the system. So when you square it, it will tell you that probability, 3/4 spin up and 1/4 down, or something like that. And it allows, this wave function allows the calculations to proceed along the lines of Newton's equations, but you solve, in quantum physics, the objective of all the exercises is to solve Schrödinger's equations. He came up with this as well, and I'll tell you in a minute, for the wave function. So the second postulate I already gave away is the probability of being in a given state is proportional to the square of the wave function times dV is the volume element. So you can think about it as a probability density as a function of position and time. It can change, evolves over time and in space. The easiest intuitive way of thinking about it is again in terms of clouds. So if you sometimes stare at the clouds in the summer, you lie on the ground and just look up, you can see the clouds flowing through the atmosphere and changing shape sometimes, you know, spreading or sometimes collapsing or merging with other clouds. It's a bit like this. So you can think about this as a probability of gases in a cloud. And that represents an electron or some other quantum object. Okay, so the third postulate is really weird, and I can only tell you that you have to spend 3 semesters in physics to master this kind of thing. It basically replaces concepts which are intuitively obvious to us, like position, momentum, energy, angular momentum, acceleration. You know from high school physics, right? You know and hate these things, but so in quantum mechanics, these concepts are replaced by operators, called Hermitian operators, special types of differential operators. Like momentum is now, this is an x component of momentum, so it would be in high school physics would be mass times Vx, right? V sub x, would be Planck constant divided by 2 pi, I square root of minus 1. This is partial derivative with respect to x. I don't have the time to explain to you why it is so, but it makes sense. and this is the formula for the energy in quantum mechanics. In classical mechanics, energy would be potential energy, right? V of whatever, x, plus kinetic energy, which is mv squared divided by 2, right? Kinetic energy. Mass, velocity squared divided by 2. This is quantum mechanical energy. This is the kinetic energy, second derivative with respect to position times all that stuff, plus d of x. All right, so that's the third postulate. Just postulate, take it or leave it. If you don't like it, you're not going to succeed in quantum mechanics. It's a drastic, it's a revolutionary departure. And finally, the last postulate of quantum mechanics is the Schrödinger equation, which replaces Newton's equations. Newton's equations, if you remember, the second law of Newton is mass times acceleration equals the force, right? So you can calculate the force if you know the acceleration, or vice versa. If you know the force, you can figure out acceleration. You can integrate it, get the velocity. You can integrate it again, get the trajectory, x as a function of t. To do the same in quantum mechanics, you solve this equation. It doesn't look too appealing, but it is what it is. So it's an evolution equation for the wave function, psi, if you can see psi. Evolution because it's time derivative, so it tells you how it changes in time. And the change in time depends on the energy formula here. It's called the Hamiltonian. And there's actually a beautiful, super elegant parallel to classical mechanics in the sense of Hamilton's equations. Hamilton's equations improved on Newton's equations. They're much more symmetrical and general. So this is in the sense of Hamilton's equation. A little anecdote again. This equation Schrödinger came up with when he went on winter vacation skiing in Gstaad in Switzerland. So he spent 2 weeks thinking about it. So you see, sometimes like patent office, you know, Schrödinger goes on a vacation, solves one of the deepest problems in science. This is a so-called stationary equation. So that means eventually things settle and they don't evolve anymore. It's a stationary state. It's like electrons just going around, around, around. So you solve it like this. I'll skip all of this. By the way, Dirac shared his Nobel Prize with Schrödinger, which is unfair because he deserved. He was one of the most brilliant physicist at the time too. And he, as I mentioned to you, Dirac introduced relativistic concepts to quantum mechanics, among other things. Introduced also an incredibly elegant formulation. Skip that, it's a little bit too... So what happened after was an extension to more and more complex systems. In other words, Niels Bohr looked at hydrogen atom, and then helium, and then you add electrons, make bigger and bigger molecules or ions, and eventually you build molecules. So the same equations were extended to chemistry to explain chemical bonds, covalent bonds in particular, where the electrons are shared. It's a wave function that connects the two atoms in the molecule, and these were the equations which have names after the people who introduced them. So Dirac, Hartree, Fock. These are equations that if you ask anybody in the Department of Chemistry, do they know it? For sure, they solved the Dirac, Hartree, Fock equations, which are relativistic equations for molecules with many electrons, some being shared between atoms. Right? You have just Dirac, Hartree, and Fock. These three guys. And now we have computer programs that, because this is very complicated. You can't, at that point, you cannot solve anything by hand. It's just impossible. You know? So now we have very accurate computer programs which give you the, as you solve it, you get the energies of molecules, excited states of molecules. They give you the bond distances, angles, everything. You can figure out exactly. And I don't know if you follow the news, but in recent days or weeks, there were some news releases about experimentalists being able to manipulate one atom at a time and even see the bond, you know, by little tips, a single atom at the tip. And so all of this, that was like very airy stuff a century ago, or 90 years ago. Now it's, we can touch it, we can do it, we can manipulate it. Okay, and I mentioned spin. I'm winding down, so let me just finish the story, because the rest is, the last 70, 80 years, it was a lot of work. But nothing as fundamental as I described to you. Now what we've found is that solids, so why is this important for biology? Because we're now going into larger things. Not just a single electron or atom or molecule even. Now we have arrangements of atoms or molecules in the lattice forming a solid. And in these solids, everything is quantized again. So waves of electronic charges are quantized. Lattice vibrations are quantized, called phonons. Spin waves, spins, you know, go up and down in a wave. And these are called spin waves. And, or magnons, and some other ones. Fancy names for all of these, but bottom line is that we are getting to microscopic objects, and if you inspect them carefully, you will see signatures of quantization in every aspect of them. So quantum mechanics is not limited to a single electron, ha ha ha, you know. But pretty much every object, of course, we have to talk about temperature later on, not today, on Thursday. And let me just say, I'll skip that also because it's a bit more intricate. This diagram gives rise to all we know about semiconductors, all the semiconductor technologies based on this Fermi-Dirac statistics. And yeah, it's probably better to say, yeah, we'll stop at this point. I mentioned to you that solids are quantum as well. So crystals, magnets, etc., etc. We'll continue the story and move into biology on Thursday. So now you know everything about quantum mechanics that you didn't want to know.
So what I wanted to say, you're probably wondering, well, there's an exam, and you know, like, I'm so far from being. So you don't have to know formulas. You're expected to know really big picture ideas that are relevant to you, like how do you compare to an electric light bulb? How does your brain compare?
Oh, we'll come to that.
Things like that, which have obvious relevance to your life. And when you go to a party and it gets beyond 10 p.m. and nobody else has anything interesting to say, suddenly the focus is on you because you know all this cool stuff, right? So that's the kind of thing that we're gonna, test you on. You're not gonna test you on memorizing formulas or really knowing detailed physics because you only have 4 hours, right? So it's not possible. And you're starting from very different points, and we want to make it fair for all of you. So if you think of it that way, like, geez, what should I study, Like, think of the idea of all students starting at the same point, right? And how much could you learn about this in a 4-hour period? And that's what we're going to test. And stuff that actually matters and that you'll care about later and that will be interesting to talk about. So we're not going to ask you to memorize names. Like, we're not going to say, okay, list everybody who was in that picture. All the Nobel Prize winners. We're not going to ask that. Okay? So.
And by the way, we'll move on from physics to other biology anyway, so.
Right.
This was probably most outside of your comfort zone that you will see.
Right. So I didn't want you to lie awake at night worrying about this.
And please come back.
Yeah. No one has ever complained about the quantum biology part
Really?
of the exam. Right. We've never had any complaints about it. So.
Relax.
Yeah. Except, there is one thing that I think you're asked to choose 4 out of 7 or something like that. Don't do them all. In other words, it plainly says on the first page, just pick
choose
4.
What, 4? 4 questions out of 5 or 7.
Yeah. So that's the only thing. So if you're very sleepy on that day, and you're the only person who answers every question, then generally what we do is we take your best 4 or whatever. But please don't do that because it sort of makes me sad when the only instruction on that part of the exam is choose 4, and you do every question. So don't do that, okay? So yeah.
Answer everyone just so you can make sure you have the best options.
Well, if you do it on purpose as a kind of mental challenge to yourself, that's okay. But don't do it by accident. Yeah. Okay, great. So
see you Thursday.
Yeah, see you Thursday. Yeah.